Hello! Finally, it's time for us to talk about E is equals to mc squared. It all started with who else but Robert Einstein. So Einstein was thinking about his pet topic, relativity, when he realized something very interesting. It seems like the mass of an object should increase as the object gains Ke. For example, comparing a moving bullet and a bullet at rest, because the moving bullet has more Ke, its mass should be larger than when it's at rest. Oh, really? So how much heavier would it be? According to E is equals to mc squared, the gain in mass of a system should be equal to the gain in energy of the system divided by c squared. C is, of course, the speed of light. C squared is, of course, a very big number. So unless delta E is also very big, if not, delta M may not be large enough to be observable. But conceptually, if you have a mug of hot water and you let it cool down, its mass after it has cooled down should be smaller than its mass when it was hot. Why? Because when it was hot, the water molecules are jiggling about with higher Ke, isn't it? The internal energy, the microscopic Ke. After it has cooled down, all the water molecules will have lost some Ke. So if the system has less energy now, its mass should be smaller. Now if E is equals to mc squared applies for Ke and internal energy, then it should also apply for electrical and light energy. So if you have a torchlight containing a battery which stores electrical energy, and then you shine the torch, so you start to convert the electrical energy into light energy, but the light is leaving the torch, you see. So after some time, the torch will contain less energy than before. E is equals to mc squared predicts that this torch should weigh less than this torch. E is equals to mc squared should apply to magnetic potential energy as well. If you have two magnets, north poles facing each other, when you bring them closer together, there's magnetic potential energy stored in them, right? Which means this system has gained energy. So these two magnets, when they're closer together, should have a larger mass than when they were far, far apart, right? Because you got to do work, remember, to push them closer together. So you have input energy into the system. Correspondingly, the mass of the system should increase. So if repulsive forces can bring about an increase in mass, what about attractive forces? Take for example a proton and an electron. If we let them come together and form the hydrogen atom, then the electrical potential energy now is less than when they were far, far apart. Remember, we have some negative electrical potential energy in this system. But if they are far, far apart, the electrical potential energy is zero. So the system has a lower energy here than here, which means the mass of a hydrogen atom should be less than the mass of a proton plus the mass of an electron. Alright, so enough of predictions. Why don't we just measure the mass of a hydrogen atom and measure the mass of a proton and an electron and see if there's any difference? But the change in mass is the change in energy divided by c squared, you see. So for all the examples given so far, the change in mass is too tiny to be detectable. For example, if the torchlight is emitting light at the rate of 1 watt, then even after 1 minute, you lost only 60 joules. E is equals to mc squared predicts that the mass of the torchlight should decrease by 10 to the power of negative 16 kg. There's no weighing scale in this world that's sensitive enough to detect this difference in mass. You can heat up water, you can freeze water, but the heat transfer required is only like a few kilojoules. So again, the change in mass is too small. What about the coming together of the electron and proton to form a hydrogen atom? Let's say we are trying to form 1 mole of hydrogen atoms. Now remember, the ionization energy of hydrogen is 13.6 electron volt. So if you are talking about 1 mole, you take this number times the Avogadro's constant, you end up with this number. So 1 mole of hydrogen has a mass of 1 gram, right? So we are talking about a difference of 10 to the power of negative 11 kilogram out of 1 gram, which is a tiny, tiny fraction. So the percentage difference is too small to be measurable. I see. Albert Einstein is a con man, right? He anyhow say E is equals to mc squared because he knows nobody can prove him wrong anyway. Well. We're talking about nuclear physics now, right? So in the field of nuclear physics, we found evidence for Einstein's E is equals to mc squared. See you in the next video. Ta-ta!